Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to identify acid-base conjugate pairs. Now, no, this actually doesn't have anything to do with verb tenses, although we already know that chemistry does have a language of its own. We need to actually write some chemical equation and identify those pairs. So let's get started. Let's get a good working chemical definition for conjugate acids and bases. Now, conjugate acids and bases come in pairs, and they are related by the transfer of a proton. Now, this is easier to see when we actually look at a chemical reaction. So let's take a look at what happens when we put nitrous acid in an aqueous solution. Here is our nitrous acid. As the name implies, it is going to act as an acid in solution. Now, remembering our Bronsted-Lowry definitions of acids and bases, our acid is going to donate a proton. Now, the question is, where is it going to donate that proton? And the answer is, it is going to give that proton to water. So here is our acidic proton. It is going to be given over to water, and what we get is the hydronium ion right here. And of course, what's left of our acid is our nitrite. Now, once our nitrous acid has donated a proton, it is no longer an acid. It becomes the conjugate base. You can see that both your nitrous acid and your nitrite are related by a proton. We can do the same thing with our water molecule in this chemical reaction. Water, in this case, has accepted a proton. According to Bronsted-Lowry, this makes water a base. Once it has accepted that proton, it becomes the hydronium ion. That is its conjugate acid. Again, this pair is related by the transfer of a proton. Our conjugate acids and bases are not only true for when we put an acid in aqueous solution, but also when we put bases in aqueous solution. So let's take a look at what happens when we put ammonia in an aqueous solution. Here is our ammonia molecule. It is going to accept a proton from water. That makes it a base. So therefore, where is its conjugate acid? Right here, the ammonium ion. Ammonia and the ammonium ion are a conjugate pair. But of course, just like we did for nitrous acid, we can do the conjugate pair for water. In this reaction, water is donating a proton. That means it is acting as an acid. Once it donates that proton, hydroxide is its conjugate base. So water and hydroxide are another conjugate pair. These two reactions dealt with a weak acid in water and a weak base in water, but we can find conjugate pairs even if we have a strong acid or a strong base. Let's take a look at what happens when we put hydrobromic acid in water. Now, hydrobromic acid is a strong acid, but of course, acting as an acid, it is going to donate a proton to water. This makes the bromide ion the conjugate base for hydrobromic acid. So hydrobromic acid and the bromide ion are a conjugate pair. Let's determine what's going on with water in this reaction. Water is accepting a proton from hydrobromic acid. It is acting as a base. Once it accepts that proton, it becomes a hydronium ion. So here is the conjugate acid. So just like we saw with nitrous acid, water is acting as a base, The hydronium acid is its conjugate acid. Now, another concept I want to introduce is the relative strength of your conjugate acids and bases. The stronger the acid or base that you're starting with, the weaker its conjugate is going to be. The converse is also true. If you start with a weak acid or base, then its conjugate acid or base is going to be stronger. So let's go back to our strong acid, our hydrobromic acid, and let's assign relative strengths and weaknesses. We already know that hydrobromic acid is a strong acid. Not only is it on our list of common strong acids, but also it completely dissociates in water. That means that its conjugate base is going to be very weak. Its conjugate base is the bromide ion, so we will call that a weak conjugate base. You can see this is true also from the chemical equation. We do not have the reverse reaction occurring. The bromide ion is not going to take a proton from the hydronium ion. This does not occur because the bromide ion is such a weak conjugate base. It doesn't have the strength to take a proton from hydronium. Let's do the same thing with water in this reaction. Water is acting as a base, but of course water is a very weak base. That means that its conjugate is going to be strong. Of course, its conjugate is the hydronium ion. When finding conjugate acid and base pairs, obviously you need to be very comfortable with your definition of what an acid or a base is. Now, in this video, I just used the Bronsted-Lowry definition. If you need a refresher on that, I do have a video going over all the different definitions for acids and bases. Conjugate pairs are going to become very important when we start talking about buffers. But the first thing we need to be able to do is to identify the conjugate pairs. Now, in my next video, we're really going to dive deep into the nature of water, and specifically, we're talking about the autoionization of water. So I hope you'll join me for that. Thanks so much for watching.